rocket ships, supersonic speeds, pressure suits, escape velocity, the vocabulary of a new era. Not a Buck Rogers era in a science fiction world, but an age having its foundations in research of the type underway at the Aeromedical Laboratory, Wright-Patterson Air Force Base. This is the story of one piece of the jigsaw puzzle of upper air knowledge that the Air Research and Development Command is fitting together. In the Aeromedical Laboratory, white mice are prepared for their forthcoming ride in a rocket to a height of 37 miles. They are given a chance to familiarize themselves with their environment inside the rocket, an aluminum drum capped with plexiglass. Special timing switches ensure that rotation of the drum inside the rocket starts at the right moment during the flight. But mice are not the only passengers. 2 monkeys will also go along. On the ground floor of the lab, the nose section of the rocket is fitted together. A motion picture camera is inside this reinforced box, and by using a front surface mirror, it photographs the activities of the mice while the rocket is in flight. The mouse container slides in next to the mirror. Inside the container, a camera test reveals how the mice act under normal gravity. The aluminum drum is divided into 2 containers by a plexiglass wall, and in the rear section, a shelf fitted with a tiny flange on the end projects into the compartment. As the drum rotates, the mouse can ride with it until the normal pull of gravity, or 1G, makes hanging on impossible. All tow holds are eliminated in the front section, so the G-force of normal gravity holds the front mouse at the bottom, exactly what the mouse is used to. The ball is a handy reference indicating the direction, but not the strength, of the G-force holding the mice. It is used later to detect rotation of the rocket while in flight. Between the mouse container and the camera fit an oxygen bottle and a carbon dioxide absorber. These create a sea level environment throughout the trip. At the tip of the nose, a dynamotor provides electrical power. Below, telemetering transmitters send out data on blood pressure in the monkeys and temperature and pressure in the rocket. Next, a monkey seat. Camera, oxygen bottle, carbon dioxide absorber, mouse container, and a second prone position monkey seat. At the bottom is the beacon, a transmitter sending a continuous record of the rocket's position. Telemetering antennae project from the tip of the airtight nose cone. The nose section is 7 feet high and made of aluminum to save weight. The rocket is a high-altitude research type called the Aerobee. On its tail is a booster which gives the rocket an additional upward thrust during launching, falling away at 1,000 feet when exhausted. The motor is simply a combustion chamber where fuel and oxidizer are mixed under pressure. At the base of the nose section, 2 parachutes are built in behind the beacon to recover the nose cone when the rocket fuel is expended. Aeromedical scientists conduct the flight at the Holloman Air Development Center in central New Mexico. The animals are prepared inside this building prior to firing. The experiment has 3 specific purposes. First, to test the practicability of a protective and escape capsule in a rocket flight. The second is to get a graphic and pictorial record of the effect of the rocket's flight accelerations on animal physiology. Man might be affected in the same way as the animals in the test. The third is to find what effect short exposure to sub-gravity has on animals inside a sealed nose capsule. The animals are being taken to the launching tower. At the launching tower, a check is made to assure proper operation of the telemetering transmitters. The technician holds a temporary antenna which will be replaced by the one in the nose cone. Frequency modulation signals from the rocket are picked up by this antenna on the blockhouse. Then, tuned by a technician inside with the aid of oscilloscope patterns on the telemetering receiver. and ultimately appear as lines on a graphic recorder which show changes in arterial and venous pressures in one of the monkeys. The nose fastens on by bolts to the body of the rocket. It is really just a framework now, but when the rocket is in launching position in the tower, the animals and equipment will be added. After the Aerobee is fueled, lifting to firing position begins. It's a slow job and has to be. Careless handling might ignite the fuel prematurely, spelling disaster for the experiment. 4 years of research and 7 rocket launchings preceded the firing of Aerobee 3. 5 B-2 rockets gave some good flight information, but the parachutes failed repeatedly. The results showed that if the parachutes would work, the job could be done. Then 2 Aerobees were fired. In the first, the parachute again failed. In the second, the parachute worked, but other difficulties prevented success. And now the 8th in the series, Aeromedical Aerobee 3. Monkeys were chosen for the test because they most nearly approximate the physiological structure of man, and reactions they have to the rocket flight will be indicative of a normal man's reaction. Mice were chosen for the subgravity tests because they were the smallest available animals which could fit into the limited free space inside the rocket. With the animals on the scene, loading of the nose section can begin. The animals are carefully placed in their assigned spaces. Nylon safety harnesses and sponge rubber crash beds guard the monkeys against landing shock. One monkey is anesthetized, the other given a sedative to make sure undisturbed physiological data is obtained and to prevent discomfort. The aluminum nose cone slides on from the top. All is ready. Months of research and planning hang in the balance. The firing officer alerts the area with orange-colored flares. One question remains: will everything work? In the blockhouse control center, it's only a matter of seconds. 5 seconds. 4, 3, 2, 1, fire! Acceleration after takeoff subjects the mice to 4G, or 4 times the normal pull of gravity. Normally, the mice weigh 30 grams each. Now they weigh 4 times 30, or 120 grams each, and their legs are unable to support them. Fighter pilots are often subjected to 5 and 6 Gs without ill effect. By the time all fuel is burned, the rocket is hurtling upward at more than 1,900 miles per hour. Without support from the rocket motor, the missile actually floats upward, gradually losing speed because of the pull of gravity. The mice float in their containers, evidenced by the ball no longer held at the bottom of the drum. The first mouse is more disturbed than the second because the second is better able to orient himself by reference to the shelf. The 120-gram downward pull on the mice during takeoff is replaced now by only a 1-gram sideways thrust caused by the slow rotation of the rocket. At 43 seconds after burnout, a timing switch starts the drum rotating again, and the confusion of the mice becomes more pronounced. Rotation of the rocket still keeps the ball on the side and tends to hold the mice lightly against the plexiglass wall. But the mouse in the rear compartment easily clings to and rides around on the shelf, a feat he could not do under normal 1G force. Although the rocket is still coasting upward, The mice feel no pull of gravity. To them, there is no up or down. The front mouse is confused by the unexpected motion caused by his actions, the effects of which are magnified 30 times. The nose cone is separated by a small powder charge, and a ribbon drag parachute has come out simultaneously, but has no effect yet. For all practical purposes, the nose is falling free. At this time, weight diminishes to the lowest point in the test. You have momentarily experienced nearly the same weightless feeling when a high-speed elevator starts down. The nose is beginning to slow up now. At a lower altitude, the ribbon parachute bites into denser air. The nose is decelerating rapidly now. Subgravity quickly gives way to decelerating g-forces of 5 and 4g, gradually reducing to normal 1g, and consequently, normal reaction to movement. At 20,000 feet, a second larger parachute has blossomed out, gently lowering the nose to Earth. This is the last leg of the journey. As descent is steady, the normal weight is reestablished. This brief test revealed no reason why man cannot fly 37 miles up in a rocket. No harmful effects occurred, and the test showed that the great environmental changes have no effect on life in a sealed capsule. Return and safe recovery of a capsule has proved practical. No time can be wasted in getting the animals out. The scorching New Mexico sun can still harm the animals at this late stage. So to save time, tin snips and a hacksaw make short work of the nose cone. Removing the cone intact would delay recovery too long. Both monkeys are still a little dreamy from the sedative and anesthetic, but they are completely unharmed. Of course, one test doesn't give all the answers, but it does point the way for others. Future studies using high-altitude balloons and longer-range rockets will be made to discover the effect of prolonged exposure to cosmic radiation and the subgravity state. This study is one of several being conducted by Air Force research laboratories. Their work is coordinated by an Upper Air Research Committee of the Air Research and Development Command. The scientists, with the animals, move back to the laboratory. Aerobee 3 flew according to plan, bringing back its passengers to lead normal animal lives. They've earned their titles as the world's first rocket passengers. One successful experiment in a whole program of experiments. A program leading to man's mastery of the air miles above the Earth, and eventually, perhaps, to Earth's venture into space.